Assalamualaikum dan salam sejahtera. Anda seperti biasa sedang menonton Sudut Pandang. Hari ini sekali lagi saya berbangga kerana ada seorang saintis terkemuka dunia yang datang untuk berbicara dengan sudut pandang, dan oleh itu saya ingin meminta kebenaran untuk berbicara dalam bahasa Inggeris. With that, I would like to welcome the one and only Professor Roger Kornberg, the Nobel Prize winner for 2006 for chemistry. He didn't share it with anybody. Usually, it's usual for you to see the prize being shared by two persons. But for 2006 chemistry, it was you and you alone. Surely the achievement is great for the committee to award you such prize. And I would try to make this simple. It's basically about DNA. And thanks to Hollywood, DNA is not such a foreign term because we watch crime scene investigation, CSI, all the time. And we know they use DNA to catch the bad guys. However, we do have to go a little bit back towards our primary school days and to look at enzymes and virus and cells. So please correct me if I've got this wrong. It's basically, your research is about how DNA is replicated by an enzyme, for example, RNA, and how that later goes all the way to form proteins, which if we don't have that being done in our cells all the time, we would just wither and die. Not just us, but maybe the yeast that you use as your subject and other plants and organisms. Is that right?
That's exactly right. And if I may say the same thing in a slightly different way, DNA contains all the information for constructing and for the function of every living thing. So we are nothing more or less than our DNA. Every component of our body and every capacity that we possess is written in our DNA. The problem is how to execute those instructions. That is the role of RNA, and that is the subject of my work.
How did you get started in this? We know you have a very strong influence in the form of your late dad. And do you see that it's only natural for you to pick this up and move on?
Not at all, not at all. In fact, I actually began my career in science in another field. I started out as a chemical physicist, and I studied a problem in molecular motion, unrelated to DNA. The molecules I studied were fat molecules at the time. They had nothing to do with genetics. I became interested in DNA when, at a subsequent stage of my training, I went to a laboratory in Cambridge, England, in order to learn a technique called X-ray diffraction that was not available to me in the United States at the time, certainly not in the university where I studied at the time. And I was looking for a problem to practice this technique. It turned out that there was an unsolved problem that I could explain to you briefly related to DNA. And so I began actually really using it only as a vehicle for learning something else. Somewhere along the way I became interested in the function of DNA. I became interested in how the information in DNA is expressed to give rise to a living, breathing organism. And that led me to study the process of making RNA from DNA, to which I referred.
Not just scientists, but a lot of people around the world would like to have the key to the secret of life. And DNA is greatly linked to that because, like you said earlier, everything is coded there in our genes, for example. But what you have done, correct me if I'm wrong again, this is quite a technical subject for me, is look at the process. You even captured the process and film a snapshot of it. That's why it's so important and crucial what you are doing and what you have done.
So you're quite right that we wanted to understand how the information in DNA is expressed. We knew that the process involves copying the genetic information from the form called DNA into a closely related form that we call RNA, we knew that that is the key decision point in the process of the use of genetic information. And we also knew that in order both to understand and control the process, we needed to discover how it works. You can't figure out how anything works if you cannot see it and analyze it in detail. So the goal of our research was to literally visualize the process. That took us almost 30 years, but we eventually succeeded.
And these are very, very small things to study. You know, DNA itself, and you're looking at the atoms that made up the molecules, for example, 30,000 atoms, for example, involved in the enzyme itself, and Synchrotron, the machine. You said that is very crucial to what you have achieved. How crucial was it?
So let me first explain. The scale is indeed very small. So the object that we photographed is 1/1000th of a meter in size. It is made up of 30,000 individual atoms, and our picture shows the location of every one of those 30,000 atoms on the scale, as I say, of 1/1000th of a meter. The only way to reveal that information was with the use of X-rays that are produced in what is called a synchrotron.
Yes.
There are a few such places in the world, and fortunately for us, one is down the road, just a few miles away, at Stanford, at what is called the Stanford Synchrotron Radiation Laboratory.
So there's you diffraction process involved, and then the computer will analyze the result of that particular diffraction.
So the way in which we produce the picture is by shining X-rays on this very small molecule, as I say, 1/1000th of a meter in size. Then we record the pattern of the X-rays bouncing off the molecule, and then we use a computer to analyze that pattern and recreate an image of the molecule.
I think I've managed to pass this particular subject for now. We need to go for a short break, but once we come back, where do we go from here? Because this is very, very crucial in biotechnology, for example, but what do we do with it? This is fundamental science, and after fundamental science, there's applied science, for example, commercialization. We'll discuss that after this short break. Thank you for still watching Sudut Pandang. I'm still here with the Nobel Prize winner for Chemistry 2006, Professor. We have explained briefly about what your research is all about, DNA, RNA, transcription, the secrets of life, but the importance of it in everyday life, for example. We know that without that particular process, we would just die, for example. Organisms would just wither and die. But through science, we will get other products or inventions and innovations. Where do you think your particular finding would bring commercialization of products and innovation after this?
So there are doubtless many applications of the knowledge that we have acquired because of its central role. I can give you a couple of examples.
Yes.
But as I say, I'm certain that over the years there will be many more. One obvious example that relates to a problem of current great interest is stem cell biology. You and your viewers are doubtless aware there's great interest in stem cells for the cure of diseases which require the replacement of diseased tissues. Or the substitution of a body part that has been
Organs,
lost for some reason. In order to convert a stem cell into a desired tissue, it is necessary to bring about the expression of the appropriate instructions in the cell. If you want to convert a stem cell into a muscle cell, you must express the component of the genome in the stem cell that directs, that specifies, that encodes the architecture of a muscle cell. Conversely, if you wish to turn the stem cell into a skin cell, you must not express the muscle potential, but you must express the skin potential. That process of expression is one and the same with what we have been discussing. It is transcription. The decision whether to make a skin cell or a muscle cell depends on the appropriate control of transcription. Our work has made possible the very control that is required in this case.
So we can now manipulate it to our advantage, the process of transcriptions that happen at the cellular level to, grow some tissues or organs, for example. Is that what you're saying?
We have, I think, overcome some of the main obstacles to such control. In some cases, it may even be possible to do it today. Certainly, it will be possible in every case in the foreseeable future. That, as I say, is one example.
Yes.
If you would like, another very straightforward example is in the cure of viral disease. So we all know that bacterial disease is largely eradicated by the use of antibiotics. These are wonder drugs, and almost any bacterial infection can be treated successfully with antibiotics. But there are no treatments for viral diseases. There are one or two drugs on the market which have limited effectiveness, but there are hundreds of viruses that infect humans. We believe that our knowledge of transcription, indeed, that the structure we have determined, the organization of atoms in the key molecule, will serve as a basis now, and I should say rapidly in the very near future, for the creation of very powerful drugs to combat viral disease.
AIDS cure, for example?
Absolutely. We will make drugs that will cure viral disease.
Going back to the tissue generating part, cancer, for example, because what you have studied shows that the process is very specific, very, there's no room for error. Nature has put it in such a way. That's what you also are finding, right?
That's correct. Cancer represents an example where this very same process that we discuss, what we are speaking of, has gone awry. A mistake has been made, and the wrong genes are transcribed, the wrong information is expressed in the wrong cell at the wrong time. In order to correct that, we must once again exercise control. Knowledge of the mechanism that we have gained permits us to exercise such control.
There you go. No wonder the Nobel Prize for Medicine in 2006 was also linked to the process that you have discovered.
That's true.
Yeah. So you have, through thick and thin, stayed on with fundamental research. But even in Malaysia, our scientists sometimes and our administrators of higher institutions are debating on percentages of focus on applied science, percentages of focus on fundamental science. What advice would you have for us, for example?
I have a very strong opinion in this regard. I think that it is the place of the universities here in Malaysia and everywhere in the world to make the discoveries, to do the basic research, which can then be commercialized in a pharmaceutical and all the other companies that may exploit those discoveries. The limiting factor in technology, in the cure of disease and other applications of our knowledge, is not at the level of translating discoveries into technology. The limiting factor is always the knowledge itself. Believe me, the commercial incentives are very great. Whenever a discovery is made that can be brought to market, that is done very rapidly. It is knowledge that is insufficient. It is basic science that is most needed. And I urge the government and the people of Malaysia to support basic science in their universities, to allow the commercialization to take place freely within the setting of the industry that will be greatly stimulated by the research done in the universities.
We must have patience and perseverance because your research took 30 years.
Basic science represents an investment in the future. More than that, it represents an investment in the people. My advice to Malaysia, to any developing country, and to every developed country is to invest in the future and above all invest in the people who are the future. That is best done by laying the foundation which one can do in the setting of the universities, laying an intellectual basis for the country.
We're going to talk more, but I have to go for the last commercial break. But once we come back, we'll tease Professor Kornberg on certain issues like ethics in biotechnology, for example, because Malaysia has declared that we're going to go in a big way into biotechnology, but certain issues, are still up there in the air to be discussed. We'll discuss that with a Nobel Prize winner, Chemistry 2006, after this short break. We are still in Sudut Pandang discussing a very pertinent issue, biotechnology, because we do have the Nobel Prize winner for 2006 chemistry, Professor Kornberg here, and the ethics side of things. I know, people always say that the scientists will stay in the lab and, they don't think about all this. They pursue a specific line of knowledge and all that. But surely, in this day and age, you must also be thinking about the impact of things, of discoveries and all that. And people in this side of the world, we all know about the leadership maybe, and some of us worry about super genetically modified bugs, for example, or even the GMOs for big juicy tomatoes, but genetically modified, for example. What are your views on them?
The role of a scientist is exactly the same as that of every other member of society in regard to these ethical questions. So the scientist can neither ignore them nor alone make the decisions. Scientists have the job of producing knowledge and then of communicating that to the public and then functioning as a member of the public, neither more nor less important than any other one, in arriving at an appropriate decision how best to exploit the knowledge. If you will, the situation is perfectly analogous to that of nuclear physics. It was primarily physicists who developed nuclear weapons, but it is not primarily physicists who decide how to use them. They should have a voice, like every other member of society, but no more or less than that.
Is that why you are joining the Bridges series, for example, with this series done by the International Peace Foundation, so that you can go out there to this area like Southeast Asia, for example, to create awareness about knowledge?
I think the first purpose of Bridges is education, and it is with the idea that education is an important step towards creating tolerance, towards communication between people, and ultimately creating conditions for a more peaceful future for all of us. I gladly accepted this invitation with the idea of contributing to that noble effort.
Yeah, my next question would be, Malaysia too would like to have its Nobel winner sometime in the future. And I know this is your first visit to Malaysia and your brief time here, but what would your advice be? Do you know, I think scientists out there in America, they don't do research because they want to win prizes, for example, because they're hungry for the answer to that specific question. Looking at, just like you said before, you were not looking at DNA before, but you were trying to solve a problem. Do you think that is the fundamental basic that we should start from school, that, hey, this is not about getting A's or anything, but if you learn chemistry, these are the potential problem-solving solutions available, for example?
I think you've said it very well. I think in the first place that there will be Malaysian, also Thai, Chinese, other laureates of, Nobel laureates of other nationalities in the future. Indeed, I would predict that someday probably the majority of Nobel laureates will come from Asia rather than from Europe and America, because the talent, the interest can be found here and elsewhere in Asia. The limiting factor is the support of young people to pursue their curiosity, to indulge a passion for science or indeed any other intellectual activity. I can assure you that if Malaysia invests in its young people in this way, that all good things will follow. And the Nobel Prize, for sure, but I would say not even chief among them.
Do you think the systems of education all around the world now put too much emphasis on results and exams, and is taking the fun and the natural spirit to learn and to want to know?
What you say is very true. It's almost tragic. When I was a child, I felt no such pressure. I didn't even do my homework.
Really?
I never bothered when I was in grade school or in college. It didn't interest me. I didn't do it, and I scraped by. But what I preserved was the interest, which was never in any way suppressed by undue pressure. I always felt I could follow my own inclination, do what I wanted, and then later in life, I had the opportunity of doing just that in the field that we have discussed. Young people today feel enormous pressure to learn specific facts, to perform on examinations in certain ways, and I think it has a harmful effect and is in some way adversely influencing their future.
We have a few minutes left, but before I go, I want to go a little bit back to the technical side of things. Where do you go from now? I mean, you got the Nobel Prize in 2006, and obviously that's for research done since the 60s, 70s, 80s, and 90s. But looking forward, in the world of transcription and 1 billionth of a divide that we were not going to be able to see, but you see it every day in your work, where do you go from here?
We have just begun. We have only scratched the surface of our subject. The great mysteries still remain to be solved, and I regard the Nobel Prize as mostly an annoyance. It has in some way interfered with my work and partly disrupted my concentration. My interest is continuing and ultimately succeeding, finally dispelling those great mysteries. And I'll give you one example that relates to what we already discussed. So one of the findings we made, I think an important discovery in the course of our work, is the existence of a true molecular computer which interprets the information which then directs transcription. It isn't enough to turn on a gene where it is required to read the relevant information for a muscle cell in a muscle cell. You must read the relevant information, turn on an appropriate gene in the right place at the right time to the right extent and in response to environmental as well as internal influences. That is a very complex decision-making process. We discovered some years ago there is a molecular device inside our cells that is present throughout nature, that is the same in humans as in plants, present in every animal in the kingdom. A molecular computer that receives all of that information and then calculates the appropriate response, delivers the signal to the machinery for transcription to achieve the desired result. We have no idea how that computer works. We know it's enormously complicated. We know that its function is of utmost importance for the very thing we discussed. For example, cancer or stem cell development. One of the main objectives of my work today is to accomplish for that molecular computer, which is vast in size compared with the RNA enzyme we studied before, the very same thing. Figure out how it works.
Thank you so much, Professor Kornberg. I'm going to have to, every now and then, check out on the Stanford University website to see the progress on that. And thank you so much. You've talked about a lot of things, but one of the things I would like to pick out is, do not worry about your grades. If you want to find out about the supercomputer in our own cells, for example, all it takes in the beginning is just the interest to know. Thank you so much, Professor Kornberg. Thanks to you, all of you at home for watching. Terima kasih banyak kerana telah menonton. Hantarkan pandangan anda sendiri kepada sudut pandang @astro.com.my. Selamat malam dan terima kasih.